Hello, this is Ernie, and in this video we'll learn how to write high-performance transactional applications with Go and DynamoDB.
Go offers many advantages, but primarily it's a language that produces small compiled binaries that run fast. DynamoDB also has a large number of benefits, but the key one is that it's a linearly scalable database that produces single-digit millisecond response times under extreme high concurrency.
Together, Go and DynamoDB offer the most optimal choice in terms of a programming language and a backend store to get Netflix-level scale out of AWS. Let's now look at how this video is organized.
First, we will describe the solution we aim to build to demonstrate the use of Go and DynamoDB. Then, we will show the typical challenges found in the modeling of data using DynamoDB, followed by an introduction to the AWS SDK for Go and the implementation of the solution's key use cases. Finally, we will explore a high concurrency scenario in which we would see both Go and DynamoDB working at scale.
Before we dive into technical details, it is best to see the shape of the final solution before we look at the implementation of its building blocks.
We'll be building the modern equivalent of a Hello World app, which is of course a to-do list management application, except that we'll make it a bit more interesting by making it multi-user, multi-list, and capable of transactional collaboration. Last but not least, it will be a command line interface app rather than a web app, so that we don't distract ourselves with web services and other concerns that aren't related to the task at hand. Our to-do list application runs on a Linux box and connects directly to DynamoDB. Such a box may be a local machine or an EC2 instance, which is what we have selected for this demo. Furthermore, we set up the DynamoDB table definitions using Terraform and then populate them with synthetic data using a Python script. Our application implements a number of use cases. First, users need the ability to identify themselves with the application either via ID or email. We abstract away from authentication, assuming that identity is managed by an external identity provider. Once we have a user identity, we can start managing lists. This includes viewing lists that the logged user has created, as well as those created by other users, creating lists from scratch, deleting lists, and selecting a list so that I can manage the items declared within that list. Once a list is selected, there are two categories of use cases: the management of guests associated with the selected list and the management of items within the selected list. When it comes to guests, I can view the list's guests, add a guest to the list, and remove a guest from the list. When it comes to items, I can view the list's items, create items, delete items, rename items, and tick and untick items, signifying whether they are still pending or done.
There are many ways to skin a cat, and likewise many ways to model a database in DynamoDB. We will look at the pros and cons of following a conventional NoSQL approach versus a more relational kind of approach.
Let's start with a NoSQL conventional model. First, we declare a table to store information about users, except for authentication details that we leave to the identity provider. Here, PK in brackets stands for partition key. Here we have the first issue. If we wanted to search users by email, we would incur a full table scan, which is slow. So we can also create a global secondary index that can map emails to user IDs. Then we define a table to declare lists. This table, other than its unique identifier, contains several attributes. the user ID attribute, which represents who owns the list, the title, the list of items declared within that list, and for each item its description and a boolean done value specifying whether it is pending or not. Then we also have an attribute to store the number of guests as a list of user IDs. And finally, we have a version attribute to manage race conditions when a list is updated in a concurrent setting. We can note here that retrieving the list that belong to a particular user would require a full table scan, in other words, a slow operation, so we can add another global secondary index to map user IDs to list IDs. Let's now look at the problems that are inherent to a model like this. First, while nesting the item data within the list is efficient both from a storage and latency perspective, it's not ideal for a high concurrency scenario in which multiple users can be collaborating on the items on the same list. This is because modifying a single item means modifying the entire list value, so the entire list needs to be somewhat locked either in a pessimistic or optimistic manner. A possible remediating alternative is to store item changes as events so that every list level update operation is additive as opposed to potentially destructive. Last, we also have the problem that searching for the lists in which a guest is a member requires a full table scan. It is not possible to use a global secondary index because the partition key has to be a primitive type and cannot be mapped from elements of a list. We'll now try to remediate the problems found in the NoSQL model by implementing a more normalized one. Here we still have the users table and its global secondary index. However, when it comes to the list table, we only keep the user ID, the title and its global secondary index. The items instead we declare in a separate discrete table. This reduces the issues of race conditions when multiple users work on multiple items declared on the same table. We also declare a separate table to map lists to guests and add a secondary global index to map guests to lists, which was the second issue we had with the NoSQL model. It does appear like we have fixed the problems found in the previous model, but in reality we have created new issues. If you look at how we have implemented the view lists use case, you will notice that the number of guests and the number of items are displayed for each list entry. Obtaining this information in the NoSQL model is much cheaper and faster, given that all we have to do is just get the size of the guests and items attributes, which are already in memory after loading a list entry. Instead, in the new normalized model, we have to fire up two separate queries for each list, one to find out the number of guests and another one to find out the number of items. This means that displaying, for example, 5 lists results in at least 15 round trips to DynamoDB. There's no perfect model. The choice depends on whether we want to prioritize storage efficiency, say over query speed, or perhaps integrity over concurrency. For our project, we selected the more normalized model because we are interested in transactional applications with high concurrency. Now, I have a surprise for you guys. I've included an extra model that I call the fundamentalist NoSQL model, and this model achieves extreme storage efficiency and rock-bottom AWS builds. In truth, all of our data could be stored in a single table. The only rigid attribute in this case would be the partition key, which we declare as a generic attribute called object ID. The absence and presence of all other attribute types would depend on the object type. For example, to represent users, we could use objects prefixed with the letter US and include the email attribute. What about the global secondary index required to look up users by email? Well, we can treat the object ID like the email and declare a reference object ID attribute to map back to the user ID.
Naturally, this lookup would require 2 round trips to DynamoDB rather than 1. Then lists and items would be modeled similarly to the way in which we did it for the initial NoSQL model. Again, we won't use this model. This is just to show the flexibility that a backend store like DynamoDB offers in terms of data modeling strategies. First, we create an IAM user with access permissions to DynamoDB, and then we log as that user and create a defined profile for it that we call DynamoDB_profile. With that profile, we define a Terraform script to create the tables we have just discussed in a programmatic fashion. After we apply the Terraform script, if we go to the DynamoDB console, we will see that the tables will have been created. Then last, we create a Python script that allows us to populate the database with synthetic data. Once we run the Python script, if we go again to the DynamoDB console, we will see that each table has sample data. In the last part, we saw how to create DynamoDB tables using Terraform and how to inject synthetic data using a Python script. Now it is the time to see how to interact with the database using Go. The AWS SDK for Go has a number of packages as shown on the screen. There is no need to remember what each package is for. We can explore the SDK in a practical manner as we will do next. Working with the AWS SDK for Go normally involves a few steps. First, we create an AWS session value specifying the desired AWS region, our profile, or whatever details allow us to authenticate with AWS. Once we have an AWS session, we create a DynamoDB value which provides a number of operations such as query, scan, etc. Each operation takes an input value and produces an output value and an error value. Let's now zoom into each stage. Here we have the creation of a session value from which we then create a DynamoDB value. The session package has a number of authentication approaches. In our case, we specify a profile, which is saved to my local machine, and a region. We may need fewer options if we're using role-based authentication in a lambda context. With these few lines of code here, we are now ready to make queries against DynamoDB. The DynamoDB value has a method for each DynamoDB operation type. For example, the query operation in this case. In turn, each operation expects a specific type of input value, which we use to define the operation's parameters, and a specific type of output value, which we use to obtain the operation's results. The operation may also return an error value, which we can test to see whether we can cast it to a specific error type and treat it accordingly. Given that Go is a statically typed language, each operation has corresponding input and output struct types that we should consider. Let's now look at the anatomy of an input value. In this example, we're looking at the use case of viewing lists by user ID, which is accomplished using a global secondary index. So at least we need to specify the original table name and the global secondary index name as well. Then we specify the query itself, which is whether the user ID attribute is equal to a provided value called v1. Naturally, we need to map v1 to a concrete value, in our case the value of a local variable. Finally, we also specify the attributes that we want DynamoDB to return and the consume capacity. Also note all of those weird string methods from the AWS package. Do they produce some bespoke AWS specific string type? Not really.
They just provide a pointer to the string as shown in the implementation of this function. Once the input value is created, we just pass it to the desired operation, which produces an output and an error. As explained before, the error may be of AWS type. In most cases, processing the output value is easy. For example, in the case of an output query type, we get a count attribute that gives us the number of items returned. The value helps define the size of a slice that we will use to store our results. We also have an items attribute which we can traverse to extract each item and map it to our type, list, using the unmarshal map function from the Dynamo attribute package.
We've just seen how to write Go code to interact with DynamoDB. Now we will look at how said code fits into our larger project.
In ModelGo, we declare the entities that we have in our business domain, like users, guests, lists, etc. We also declare a custom error interface so that we can wrap the SDK and the driver level errors. And finally, we declare the methods as an abstract interface that represent the operations that we want against our selected backend store. Just to prove that our model is independent and decoupled from a particular backend store, we implement a dummy memory implementation. In this case, only a few methods are implemented, and this is just to prove that we can swap different backend implementations. In dynamo.go, similarly to memory.go, we import the model package and implement each of the interfaces methods with DynamoDB specific code. In main.go, we implement our command line interface, which allows users to interact with our to-do list application. An interesting aspect about our implementation is that we allow users to select among different backend stores. At the moment, we have implemented a memory-based backend store and also the official DynamoDB one.
In the last part, we saw how to use the AWS SDK for Go in general, but now we will look at how the implementation of a concrete use case looks like.
The use case login with email is the one related to the use of the global secondary index called users by email. Now, implementing this use case has two parts. One is the command line interface part, and the other one is the implementation of our DynamoDB backend code. So let's get started with the command line interface. Here we have to grab the email address as an argument to the email command. And once we manage to get that value, which we will see now, just by running a quick experiment that we can get dog@doggy.com, then we can send that email into our backend implementation, which is called get users by email. And once we get that user entity from the backend, we can assign that as the current logged user. Now, we haven't implemented the backend code yet, which is what we have to do next. As we've seen before, we need to first get an input value. Then we take that input value and send it into the operation, which is query. And after that, we can process both the error and the output. In this case, we look for a general error. And also we look for a possibility that the user might not have been found, in which case the count would be 0. So if there are no errors and the count is not 0, then certainly we are in front of a found user. And for that we create an entity value for that user and then marshal the result back into that value. Then we can return that value and we see what happens now. And of course we haven't implemented any code yet for how to get that exact record from DynamoDB. So we need to specify a number of attributes to do that. At least we need the table name and the global secondary index name. And if we provide that, still we haven't got an answer, because we need to specify the query. What is it that we're looking for? So we want to match the email with a value. If we just concatenate the string, that's not gonna work. We need to define a placeholder, which is column v1, and then to that placeholder, to that variable column v1, we need to bind it, we need to link it to a variable of our own, which is in this case is the email variable that has been provided as an argument to that method. So once we do that, then of course it works.
We will now finally see the use of Go and DynamoDB in a high-performance, highly transactional scenario. We will take it slowly, make mistakes, and see what happens. We will increase DynamoDB capacity to avoid bottlenecks, but be careful, because setting 10,000 capacity units per table can get very expensive.
Here we're about to run 2 sessions representing 2 users who are going to be interacting concurrently with DynamoDB. So we have here on the top a session for user 1. Here we have a log file where we're gonna see the low-level actions, and here to the left we'll be redirecting the error stream to that log file, and we do the same here below for the second user. So let's go ahead and run this. So let's run the first one. Started, presenting the menu, and now we go to the second one here. Okay, now let's log as a user with the first one. Here, when I run the users command, we see the low-level activity here. We see that the list users method has been invoked without user ID, with a maximum of 5 items. We get the capacity that is used, which is 1. We got the time that is taken, 64 milliseconds. Now let's use Anthony 72 as the user. So we select that, number 4 on the list. Now we're logged as Anthony. We see what lists that Anthony has, so we type lists, and we see that there are a number of lists that are created as synthetic data. I'll remove an existing list, which is number 8. This one here, I'm gonna create that again from scratch. So let's go ahead and create a new list. So list create new, let's call it maybe shopping list. Okay, that list has been created. Now we can switch to that list. So I can just copy paste the now let's do this instead. Just to lists, and the list is here. So let's select that list via the token number 18. So we are inside of shopping list. We do items, there's nothing. We do guests, there are no guests. So first things first, let's assign some guests to the list. So let's see what users we have again. So let's do guest add Ronald 42, which is number 20. And let's add also Patricia 32, which is 21. So we do guests here, and those 2 guests are assigned to the list. If we do list here, we see that shopping list has 2 guests, but there are no items. So let's create some items. Item create by milk, item create by beer. So if we do items, we see some items. And now let's go into the concurrent scenario. So here I'm not logged as a user yet, So what I'm gonna do is see users, and we know that Ronald 42 and Patricia 32 are guests to that list. So let's log as Patricia then, see what lists are available, and we see that shopping list appears as one of Patricia's list, and she is there as a guest. So let's select that list number 9, and if I do items, I see the same items as Anthony. So here I can create, let's see, item create again. Let's say by flowers, item create. What else? By Nutella. Okay. We have some items here. Okay. So one of the first issues in a concurrent scenario is that of two users working on the same item. So for instance, let's say that Anthony wants to be more specific about the beer. It's not just some random beer. Okay, so if Patricia goes and buys the beer, Anthony doesn't want Patricia to buy some random beer. Okay, so he may do item rename 35 to buy, let's say, a left beer. Okay, so he may do that. Okay, let's say that he has renamed that item. Okay, it is renamed. And now Patricia, let's say that she's already shopping and she marks that item tick 13 in this case, because it's a different reference beer, as tick. Okay, so it's like, okay, I just got the beer. Maybe she bought Foster's, for instance. Yes, so she does tick that, and boom, we got an issue here, because actually just before that Anthony had renamed the item. And this is how we maintain transactional consistency, that once I grab an item, if someone else comes and makes an update, there should be, of course, a conflict. Yes. So this is reported as not found. We're reporting the low level error for in order to be practical. So it's not found because there's a problem with the search criteria. Yes, this is what it reports here. And actually what happens is that here we have version equals 0. So it was looking to update an item whose version was meant to be 0. But if I do items again here, we'll see that that is from version 1 because it has received one update. Okay. So if we switch to the implementation here of the update item method, what we'll see here is that the key update operation is setting the version to a new version, which is just a number higher than the previous version here, yes, which is 1. So this is, you can read this as version equals version plus 1. And the condition expression which makes this fail is that the version must match, so that when I grab an item and I assume one version, the moment I go ahead and write that item back to DynamoDB, the version should match, and this is not what has happened here. So this is the way that we maintain consistency here, and while two users participate on the same list. There's also another type of integrity problem, which is that, for instance, of deleting a list. Let's say that Patricia is done with the shopping and she's about to delete that list, or let's put it the other way around, because like Patricia is not the owner of the list, so it's Anthony. In fact, let's see what happens if Patricia tries to delete the list. That's an interesting, I haven't even thought about that case myself. So let's say we do lists, and I do list delete 24 shopping list. Let's see what happens. Okay, this list doesn't belong to you. That's fine. Yes, indeed, she's not supposed to delete her own lists. If I go here, do the same lists, and I am about to do delete. Sorry, we do list delete 41. Okay. Actually, this is more difficult than you may think, because what about if Patricia is still working on that list? Yes, and also the list has a number of items. So in order to delete the list, actually I have to do 3 different things. I have to say this list is about to be deleted, so don't add more items. Then so that people don't keep adding, like stop adding items to the list. Then I have to remove the items one by one, and then last I have to delete the list itself. Yes, and I sort of need to do that in a safe manner, so that there are no transactions like coming in and landing on the list as that the process happens. And to do that, let's go through the implementation of that. So we do here. We do through update list. Let's find that method. That's not that one. Delete list. Yes. Okay. Let's close that one. So we see here that we have 3 stages. First, we mark the list with an under deletion attribute. Then, second, we delete all the items in the list. And then third, we delete the list itself. Okay, and we want to do this in a transactional, safe manner, but we don't want to like log things or consume resources with no reason. Yes, we want to be sure that we do this in an efficient manner at the same time. So the way that we achieve this is that first, marking the list under deletion, it needs to be in a transactional manner. Yes, because when I'm doing that, when I'm setting when I'm setting the under deletion attribute, I don't want at the same moment to get any updates against that list, and this is why this is done with a transactional write type of operation. Okay, and what happens is that if I then go to, let's say, if I go to create an item, let's go to create item. If once that attribute is set, I have a condition that, let's look here. When an attribute is created, an item is created, that attribute should not exist. If I find the items table to contain that attribute, that means that it's about to be deleted. Okay. And the interesting part is that if I go back to my delete list method again, because my transaction is managed by that attribute, after that, when it comes to deleting the items in the list, I don't need to go into a full lockdown transactional context anymore. I can just use the, let's see, find operation. We just do a batch write item. So we do a batch to delete all of the items containing that list in one go, in one operation. And the reason, again, the reason why we have to do that transaction before is because when I'm deleting those items, if someone were to add a new item to the list while I have already got the list of items, then I will leave spare orphan items lying around in the database, which is what I don't want. So let's see this in action. So that's the easy thing. I have created here a method called slow. So I slow down the each stage, each operation in the database, so that we can see the results of a transaction failing. Let's do that. Let's start creating items here, more items, just to see the effects. We have, let's see what items we have. So that I do item create item 1, I just leave it there so I can go back via history. Here I will slow it down to 15 seconds. So everything that I do, not each command itself, but when I, for instance, when I go here to this complex delete list operation, you see that I have some slow down commands. So I have provided a slow value, which is in seconds. Then each step of the way, like before, when I enter that method, we will pause for 15 seconds, which is what I'm gonna do now, slow 15. Then just before it starts deletion, then when it's preparing to delete, then it's gonna slow down for 15 seconds again. Then here, before I delete the items in the list, it will pause for another 15 seconds. So these give us the chance to explore the transaction as it goes through and see at what moment in time it fails from the perspective of someone making queries or interacting with it in parallel. So let's go ahead and delete the list. So let's delete, and shopping list is 41. So we start that, and here we enter the method and we're sleeping for 15 seconds. Here, sleeping for 15 seconds. So now the transaction hasn't started yet, so I can still create items as Patricia. I see items. There is item 1, item 2. I can do item 3. I can do go and tick items as well. Let's tick number 3. So I do items again, just like done. Now this is just before setting the under deletion attribute. So let's create more items. So the transaction has started yet, so that's fine. I can keep adding items. Oh, boom, we got an issue here. So again, this is reported as a no match lookup criteria. But actually what happened here is that the under deletion attribute has been set. So I'm not able to add anything, but if I do items, we'll see that the list is still there. It's just that it's locked. Yes, there's no way I can add more things to it because it's marked for deletion. And now it's being deleted. Okay, now it's being deleted. And this is before deleting. So if I do list here, lists, the list is still there, so it hasn't been deleted yet. If I do lists again here, okay, the list has disappeared. The shopping list is gone. Okay. So thanks to this slow command, we could see a transaction going through step by step, and what are the dynamics and behavior from the perspective of a concurrent user.
So far we have explored transactions, but what about performance? This is what comes next. We have included low-level performance and concurrency testing capabilities via the interact command that accepts a number of threads, a variable for the number of threads that it will spawn and the number of runs that we want per thread. And what this command will do is simulate the interaction against a given list. So first we need to create a list so that the command can interact with it. So let's do that. Let's select a user, number 4, Anthony. Let's create a list then. Let's create a hacking list. The reason we call it hacking list is because we're gonna be using the facto package for Go. And that package has a random generator of sentences that have to do with hacking. We have list, hacking list is there, so let's switch to it. It's number 8, and let's start adding some items like that. So these are the kind of verbs and nouns that facto generates. You will see why in a moment. For each TTD crypt protocol. What else? With data. Encrypt file. Okay, so we have now a number of items, and with the interact command I simulate a user accessing that list and making operations against that list, but by default it's in read only. So if I run just one user for 1,000 runs, nothing's gonna change here, because all I'm doing is just accessing the list repeatedly, just getting the list of items. That's all that I'm doing. So here the way this works is that here we have the number of threads, here we have the number of runs per thread, the total, which is the multiplying threads by the number of runs. We have a timer, the elapsed time, and the unique interactions. And here are the kind of methods that we have run. So by default, in every run, we're getting a list. And then optionally, we may create new items, we may delete items that, and we do a deletion of an item right after adding a new item. And we do that so that the list remains pretty much stable in terms of number of items. We may randomly rename an item or tick and untick items. So this randomly actually is a percentage. Yeah. So we have a ratio here that we can define via the ratio command. So at the moment, 100% of all transactions are read only, but we can say that, for instance, 3% of the transactions are create ones, maybe 5%, let's say 7, so we got 10. So 10%, 7% are rename ones, and another 5 are tick and untick ones. Okay, so we can change that ratio. So if we go again here and we go interact, we will see that the list will change, because for every 100 interactions of this type, these unique interactions, some of them will be of create nature, some of them rename nature, etc. Okay, so let's run that for a bit longer. Let's do 9,000 here, and we'll see here that there are no errors, and these errors are not failures. These errors are normally transactional problems because of concurrency. Now, because we're running one thread, it's just one user accessing the same list, so there are no conflicts here. Like if we remember the beer example, where Anthony has renamed the buy beer item to buy left, and Patricia tried to tick that, and there was a conflict, that would have generated an error here. And in fact, if we increment the number of threads, we will land onto those use cases, because we will have, in the case of two threads, two users that may be looking at an item that has been updated in the meanwhile. So let's do that. If I do 2 threads, and that'll be exactly like having Anthony and Patricia interacting with the same list. So we'll do that. And we'll see here that, like in fact, in the tick and tick use case, we have some errors. Now we have some errors in the creation and deletion, and those kind of errors may also happen because I may be attempting to delete an item that has already been deleted, for instance. So we see here. I mean, these are not issues, yes, I mean, this is what you indeed expect from a transactional system, but what we need to prove is that this doesn't crash, this keeps consistent at a high scale. And here we're talking already with 2 concurrent users, we're talking about 400 transactions per second. Yes, so that's already highly transactional. And if we go now a bit crazier and we have 5 users interacting concurrently, let's do lower number of runs, because otherwise it'll never stop. So here we see we are over 1,000 transactions per second, and we see that the system can keep scaling because we have set 10,000 read and write units in DynamoDB for every table, including the global secondary indexes. So we can keep increasing the concurrency here, and the system should still scale and perform in a highly transactional scenario, which was the goal that we had set out for this video. I hope you got an idea about the benefits of using Go and DynamoDB together. This is all for today, so see you in the next video. Bye!